morning, people. I'm just setting up the screen. Yeah. So, not seeing anyone right now. Shubham Nagre. Good morning, Shubham. Prathamesh, good morning. Yesterday, we have started with the introduction to the interior of the Earth. Pratik, good morning. Avi, good morning. Sanjay, good morning. Sorry, Sachin, good morning. Yeah. So, without wasting much time, Ayush, good morning. Without wasting much time, let us move to our business end. Karthik, good morning. And let me bring up the presentation. Okay. This comes regularly basically because this is the first slide of my presentation, or this particular presentation. We have done this yesterday. We have done this yesterday, and in fact we have repeated this yesterday. And we did speak about this, that the layers of the earth. Okay, the outer layer is significantly thin, the crust, and then you have the middle layer, which occupies major part of the whole earth as such, and then you have the innermost layer, which is divided into two phases of matter, that's a liquid and a solid as such. And as far as the structure of the earth is concerned, this is how it looks. Okay, we have gone into the detail of that. A few points to be made here is that the thickness of the atmosphere, depending on the scale, obviously is going to be, and depending upon the different people who tend to um, classify the atmosphere accordingly. Because we'll be doing this in our second topic as well, wherein we would be seeing as to how different people tended to look at these things differently. In the sense, some scientists, people in the sense, some scientists would be looking out on certain components in the atmosphere. Others would be looking out in its electrical connectivity and conductivity, and others would be looking at least the last point till where the traces of atmosphere occur. So people differ as far as the thickness of the atmosphere is concerned, from 100 to some say it is 400. Here you can see it's 480. And in fact, if you go into the rarest of the cases, where you want to see, you want to take into note even the last of the element of the atmosphere, then it is somewhere around 29,000 kilometers also. So coming back to the interior of the earth, this is how it would look. And then we spoke about how seismically these discontinuities were identified, basically based on the density. And you'll see that each of these discontinuity is you'll see that the Mohos and the Gutenberg discontinuity are more popular, but then you have the ones within those layers also. That means you have the Conrad discontinuity between the upper and the lower crust. Between the crust and the mantle, you have the Moho or the Moho-Visick discontinuity. Within the upper and the lower mantle, you have the Repeti discontinuity. And of course, between the mantle and the outer core, you have the Gutenberg. And the unique one, that is unique in the sense that it's a discontinuity between a liquid phase and a solid phase as such, we call it as the layman's discontinuity as such. So this is something that we have done yesterday as well, and we were to start with this today. Uh, Actually, to speak about it in in a different way. Actually, you will see that when it comes to the interior of the earth, if we strictly go by the geography definition of geography, okay, you'll see that technically interior of the earth should not be uh, a matter of study as far as geography is concerned. And in fact, when we speak about geomorphology, because geomorphology is study of landforms, and landforms occur on the surface of the earth, so it should not be taken as a, technically I would say it should not be taken as a part of the study. But let me tell you that whatever happens on the surface is an outcome of what is happening within it, and that is why it is so very logical, it is so very empirical that we actually go into the interior of the earth, okay, and try to study what is it. It's elementary that we need to know what the interior of the earth is made up of, and it's only then that we would be able to analyze the landforms that would occur on the surface of the earth in in a better way, I would say. Um, as we have seen earlier, also in the earlier slide here, that sorry, it was seismology which was put to use when they tried to study the interior of the earth, and seismology has been significantly uh, prominent in understanding the whole course of the interior of the earth. Um, Having said that, okay, you'll see that there have been various ways in which people have tried to study. Here, people meaning geographers, geologists, seismologists, physicists, all those scientists were and are working on the study of the interior of the earth as such. There are various ways in which people try to study the interior of the earth. Okay, first, the sources on which people try to study the interior of the earth include artificial sources. Artificial in the sense physical sources. Now, what would this physical source mean? When I say physical sources, it's something that we understand with in context to physics. Say, for example, density was something which was used to understand the interior of the earth. Of course, when we say artificial, we are not actually going into the center, but then these were some properties in physics which we use to understand what may be the state as far as the interior of the earth is concerned. And of these, density is supposed to be the first one. Uh, in density, we realized that we worked out I spoke about this yesterday also, that the density of whole of the earth was worked out to be around 5.5. Yesterday, I remember I said 5, it's around 5.5. However, when we speak about the surface matter, the crustal matter as such, you'll see that on the crust, the density was around 3 to 3.5. Okay, and um, this, of course, is just beneath the major layer which covers the surface of the earth. When we are going to do rocks, we'll be coming back to this. But remember that as on today, 70% of the crust as on today is covered with sedimentary rocks. You go below the sedimentary rocks and you have crystalline rocks. You check the density of these rocks, and the density tends to be of these rocks tends to be around 3 to 3.5. It's not going to be uniform. It's going to vary with the type of rocks, when these rocks were formed, and so on and so forth. So we consider it is between 3 and 3.5. So going by this mechanism and mathematics, okay, the core eventually should have been, or could have been around, the density of the core could have been around 11. So this is how they try to estimate what should be there in the interior of the earth, how these could be changing with the use of density. Then they thought of using, some scientists used pressure, okay, with highest possible pressure as far as the center is concerned. Obviously, it was believed that the core is going to be made up of heavy metallic minerals as such. So these heavy metallic minerals, obviously we now know that nickel and iron, heaviest, amongst the heaviest of these metallic minerals, make up the core, and that is why it is abbreviated as NIFE. NIFE. Ni stands for nickel, and Fe stands for ferrous, that is iron. As far as temperature is concerned, it was seen in the earlier, I would say, few layers as far as the Earth is concerned, that temperature drops by around 2 to 3 degrees centigrade for every 100 meters as such. But as we have seen in the earlier of the slides, that going further down, okay, manually was very difficult. In fact, going beyond 8 kilometers is near to impossible, has been near to impossible. But it has been believed that as far as around 40-50 kilometers, that's at the base, I would say, of the crust, the temperatures seem to vary, and they vary significantly, in the sense that it has been seen, you must have learned this in your earlier classes, that one of the latest theory that has been approved as far as continents are concerned is the plate tectonics. Now, there are some areas wherein the margins of these plates are very active, and it has been observed that where there is this particular activity, when the margins are sliding over each other, they are going away from each other, or they're sliding past each other. These are the three types of movements as far as margins of various plates are concerned. But you go beneath these margins, whichever type of margins, you go beneath these, and you'll see that the temperatures at around 50 kilometers beneath the surface is around 500 degrees centigrade. Sorry, 1000. Because these are active margins, you'll see that this activity of the pressure involved increases the temperature, and as a consequence, the temperatures are 1000 degrees. However, those areas which have been calm, which have no history of volcanic activity, which have no history of tectonic activity, that's these plates riding, going past, or going past each other, going away from each other, you have no visible records of this happening in the last few hundreds of years as such. The base of such crusts, the temperature is literally half of that. So you have to remember that when we say these are average temperatures, okay, it's very interesting. Actually, at the face of it, it looks very confusing. It looks very mechanical. It looks very scientific. But you tend to understand the whole scenario put together. Yes, I understand it's a bit complex, but then if you start understanding it logically, it gets very interesting. In a sense, areas wherein you have a lot of tectonic activity, you go down 50 kilometers, the temperatures are high. Calm areas, the temperatures are low. Okay, so though the average temperatures at the base of the crust could be one, but you have to remember that actually the temperatures could be different. Okay, on particularly on a very large scale like this, what eventually tends to happen is that averaging does not actually suit the purpose of the cause, and that is why at times you'll see that people prefer mathematics over statistics. That is one of the major reason. Okay, but however, we are looking into both the aspects of it as such. By the time you enter the asthenosphere, okay, the margin we have said, active margins we have said, base 50 kilometers, it's around 1000 degrees. It increases by another 200 degrees by the time you enter the asthenosphere. It is believed that along the asthenosphere, the temperatures could be around 1200 degrees centigrade. Here we have to understand one thing, that it is believed that it is the lithosphere, that's the crust and the upper part of the mantle, that's called as the asthenosphere, that major source of radioactive material of the whole Earth, the major source of the radioactive material lies actually towards the upper part of. Now, why? That's for people in physics to learn. It's not, I would not consider it a scope of geography, basically, because if you remember, geography is gathering higher level information and making it easy so that the layman understands, and that is why it is called as jack of all trades. So if you ask me, sir, what are the details, I would say, please don't ask me. I am a geographer. I give you information. As far as further details are concerned, you need to go into, say, and meet specialists who are working in that particular field. In the sense, you would have people working on earthquakes, seismologists, and they could help you more. As a geographer, as I said, I need to pass on intense information made in a very, explained in a very simple way as such. Okay, so we need to understand. Yes, we get the information that it is believed that you have a higher amount of radioactive material towards the upper end of um, the earth as such. It is believed that further down, who knows, there could be, but as of today, it is believed that most of the radioactive materials are towards the upper side, and as far as the lower parts of the earth, interior of the earth are concerned, you may have very little of the radioactive material as such. Okay, then. Uh, when you go into the by the time you go into the mantle, and we have seen that the mantle is quite thick and you have to travel significantly low to get to the lower limit of the mantle, and by the time you come to the margin between mantle and the outer core, and we say and we know that this margin, this discontinuity is called as the Gutenberg's discontinuity. It is believed that the temperature there is around 3700 degrees centigrade. So from a variation of 1000 to 500 within the crust. Okay, uh, and this variation could be possible basically because the crust is very thin and it is open to normal temperature. As you go, the environment becomes more enclosed, and that is why the temperatures would be more, could be confirmingly stable, unlike what we saw, that there is a difference of nearly double the temperatures as far as the base of the crust, the base of the crust is concerned. But as you go into the mantle and further down on the discontinuity between the mantle and the outer core, the temperatures average out to be around 3700 degrees centigrade. You go further, enter the core, which is liquid, and then you reach down to the inner core, and that margin, the Lehman discontinuity, where you have the solid and the liquid part of the core meeting each other. The temperatures are supposed to be around what? It's around 4,300, and it is believed that at the center of the Earth, possibly the temperatures could be around 5,000 degrees centigrade. So these are the artificial ways in which studies of interior of the Earth are conducted, using the basis of density, using the basis of pressure, using the basis of temperature as well. Okay, pressure, we know, we spoke about it when we met last to last lecture. Pressure is measured in atmospheres, and from 1 atmosphere at the surface of the Earth, by the time you go to the center of the Earth, it could be 10 raised to 7. That's 1 crore atmospheres as such. That's going to be a huge amount of pressure that could say bring about changes as far as forms are concerned. Now here there is an important scientific fact that we need to share amongst ourselves, is that um, people believe, or scientists believe to quite an extent, that it is because of the pressure that any form of solid material or any form of or any form of mass could concentrate and would grow into a very hard solid mass as such. Recent studies say that it is not always pressure, because every mineral material as such has its own collapsing point. Beyond that point, it cannot sustain pressure and it will just deform, and it will go into a very fine this. So consequently, it also has to be understood that it has to be very hard mineral material to sustain this pressure, and that is why it is believed that as far as the center of the Earth, it is nickel and iron which play an important role as far as making up of the core is concerned. It is these properties, the metallic properties, which come up with the other features of the Earth that we experience on the surface. Say, for example, the polar arrangement, the North Pole and the South Pole, and it is also believed that the magnetic capacity of this, okay, is dependent on that. The gravitational pull of the Earth is dependent on that, and so on and so forth. So these are the physical ways of studying the interior of the Earth. Then you have the natural ways of studying the interior of the Earth. In the sense, volcanicity is one thing which people have been studying for ages. Of course, the technological development has come only recently, and you'll see that more scientific things into volcanic reading has come up in the last 100 years as such. But people believe that to quite some time, they believe that the interior of the earth is made up of a lot of liquid, and it is this liquid that keeps pouring out in the form of volcanic eruption. However, we know that not all of it. Yes, though the outer core is liquid, the reasons are different. But you'll see that even the deepest of the volcanoes just go a bit deep into the upper mantle. They don't even touch the lower mantle as such. In fact, even as far as earthquakes, when they are used to study the interior of the earth, the deepest of the earthquakes arise from the upper mantle. It's 800, 900 kilometer earthquakes are called as deep-seated earthquakes. We're going to come to that, and we're going to discuss about that as well. Having said that, you'll see that we now know that all volcanoes are not very deep, just like earthquakes. In fact, magma which keeps on emerging out of it comes in from certain sections as far as the magma, as far as the mantle is concerned, and these are called as magma chambers. Of course, you could have a huge amount of magma there, which can keep pouring out for say at times thousands of years as such. And the evolution of the Hawaiian Islands, it is every possible say it's possible that even the Indonesian islands are all because of this. Okay, so that is how volcanicity is used as far as studying the interior of the earth is concerned. And seismology, we are going to go into the details of seismology also, but that's going to be some time before which we actually get to seismology. It's going to be very interesting to study that as well. But before that, we have a few tables to be completed. Yesterday, I think we spoke about a few properties, and I said that we will not go into the temperatures. We have done the temperatures right now. How much of these, how much fraction of the Earth do these three layers overall? These three layers consist. We have done this yesterday as well. The crust is less than 1% of the mass, obviously because of the density as well. Mantle, higher density, but it's lower than the core. However, the huge bulk of the mantle is such that it, in spite of the low density, it occupies 75%, 70% of the fraction of the Earth. The core, though it is smaller, the high density that you have towards the core makes it contribute 30% of the mass. Okay? Then you'll see that the crust, of course, is broken. Mantle is plastic, and the core is semi-liquid. Some of it is liquid, some of it is solid. As what are the depths? 30 to 50 kilometers as far as core is concerned. 50 to, let us say, 3,000 kilometers is the mantle, and from 3,030 kilometers, let us say, till around 6,370 kilometers is where you would have the center of the Earth. As density, as we can see here, crust, we have also discussed about it, that the crust has a density of around 2.7. It increases to 3.5 to 5.5 by the time you go to the mantle, and it's very high when it comes to the core. It's somewhere between 10 to 12 grams per cubic centimeter. As such, chemical composition, we said that while the outer crust is more of oxidized silica, the core is more of iron and nickel. And as far as the mantle is concerned, it's a mixture of iron, it's a mixture of silica oxide. Okay, and you'll see that it's further oxidized. You'll see that crust, you have SiO2, while in mantle you have SiO4, and then you have magnesium also constituting the mantle. I don't know how many of you all have seen the movie Journey to the Center of the Earth. I have a clip of, I have the whole movie on with me. I have the HD copy of it. Had we been in college once again on campus, we could have watched this movie together. But if anyone who would be interested before that, I plan to upload it on my drive, and I could share it with you all as well. Anyway, further down, as far as temperature is concerned, we are not discarding the Kelvin degrees. We are doing it in the centigrade, and we see that at the base of the crust, it is somewhere between 500. It varies between 500 and 1,000 degrees centigrade. You go further down into the asthenosphere, it increases to 1,200. In the mantle, it is around 3,700 degrees. Outer core, it is 4,300, and by the time you go to the center of the inner core, it could be somewhere around 5,000 degrees plus as such. The pressure, as far as the atmosphere is concerned, at the crust, of course, it is 1 atmosphere, but it increases as you go down. It goes to 1,000, And it's so very simple to understand. Three zeros to one in crust, that is 1,000. Six zeros to one in mantle, that's 1,000,000, and you add one more zero, and that is how you could say the core, the temperature, sorry, the pressure in atmospheres at the core is 1 crore atmospheres. Okay, while in mantle it is 1 million. Let me tell you that though it would look only a increase of 1 0, the pressure is going to be many, many times. Let me please remind you of this as well. Okay, so that is one thing. Then we stopped at this thing yesterday, and I want to discuss this in detail, basically because this is very interesting. When I'm looking at the entire earth, what do I see? I see that iron makes up 35% of the entire earth, and another major element found on this planet is oxygen. So you'll see that iron and oxygen put together, they account for 65% of the mineral constitution of the entire earth. This is what I wanted to bring. The scale to which they vary. Okay, knowing these numbers is not a great thing, but knowing the scale at which. Okay, and you'll see that if you take the first four together, okay, silicon and magnesium, we put them together, that's 35 plus 30, 65. Silicon 80 and magnesium 90, 93. 93% of this earth, entire earth, is made up of iron, oxygen, silicon, and magnesium. You'll see that I'm not considering nickel, which makes up a significant part of the core. Now you can just imagine the scale of nickel. When I say 2%, in spite of being only 2%, I know that iron and nickel make up the core. So if the core is made up of nickel, and nickel is only 2% of that, you can imagine when I'm saying 35% iron, how much iron is there on this planet. When I say 30% of oxygen, I should be able to gauge the scale of oxygen, the volume of oxygen. Even 15% of silicon is a significant amount, 13% of magnesium is a significant amount. Okay, we gauge this from the fact that though the core is made up of iron and nickel, nickel constitutes only 2% of it. That's an interesting observation that we have to keep in mind. Then the other one, sulfur. You see a lot of sulfur pubing up as far as volcanoes are concerned. All put together is hardly 2%. And then you have calcium, aluminium, and all this would come to somewhere around 99%, leaving behind only 1% for all the others. The whole periodic table that you may have done in your school days is only 1%, rest of the periodic table. Okay, 1, 2, 3, 4, 5, 6, 7, 8 elements make up 99% of the entire earth. Now, the fascination about the interior or the constitution does not stop here. The fact that when you come to the earth's crust, the whole thing completely changes. Okay, the heavier iron, okay, you'll see is found less. In fact, you'll see that as far as the crust is concerned, something which was first in the list as far as the entire earth is concerned, it has slipped down. It has slipped down to 4 position. This also proves the fact that iron is heavy, and that is why the gravity has pulled the majority of the iron towards the center. Okay, that's a very interesting thing. On the other hand, before I come to the first two, you'll see aluminium, which we all know is a lighter material. Okay, entire earth, it comes to a proportion of only 1%, but only the crust, it comes to 8%. So the lighter elements are coming up and the heavier elements are going down. And thus, obviously, when we speak about the density of the layers, we see that the upper density is less and the inner density is obviously going to be much high as such. So that is another interesting thing. In fact, you'll see that aluminium goes up as compared to iron also. Magnesium, which was 13%, again comes to 4%. Okay, 4%. So you'll see that magnesium, what we can infer out of these numbers is magnesium is there in the crust, but it is there in the other parts, mantle particularly. It has a significant part to play as far as mantle is concerned. Yesterday, I spoke about these salts, sodium and potassium. Both of them are not at all there when we consider them amongst the first eight members as far as the entire Earth is concerned. So we could say that sodium potassium predominantly will occur in the upper layers. This will also mean that the density is going to be lesser. Okay, that leaves us with two interesting aspects. That's oxygen and silicon. Silicon, entire Earth is 15%, but when we speak about the crust, it's 28%. So interestingly, you'll see that it's no wonder that as far as the Sial and the Saima are concerned, the C in Sial and the Psi in the Saima is Si, stands for Si, that's silicon. And in fact, in the mantle also you have SiO4, silicate, a form of a silicate as such. And in fact, you'll see that oxygen, which is basically, it's a gaseous thing. So it's yes, it's a wonder to this extent, but it's no surprise that it's a gas, but it's a heavier gas. You find it not as heavy as nitrogen, but it's heavy, and that is why you'll see that it's found in the crust. Now, why is it found in the crust? Your question could be that, sir, nitrogen is 78%, and why don't you find it in the crust? Leave aside, let us say that entire Earth you may not have, but at least in the crust, if you have oxygen to this percentage, nitrogen should have shown its presence here. My answer to that would be that nitrogen is a highly inactive gas. Okay, and oxygen is a hyperactive gas, and that is why at every chance it tends to oxidize, and that is why you have this rust on iron very frequently. Okay, that's basically because iron tends to get oxidized, and you'll see that we're speaking about silicates, oxidized form of silicon, and so on and so forth. But again, interestingly enough, if I total up oxygen and silicon, what do I see? 75% of the Earth's crust is made up of oxygen and silicon. You can make sentences from what I'm saying. Okay, these are logical explanation, and this could form a text in your answer as well. Okay, so 75%, two elements make up 75% of the Earth's crust, leaving 25% for the others. Within that, again, you will see that around around 17% is made up of aluminum, iron, and magnesium. Okay, so 90% is 1, 2, 3, 4, 5 elements, and then you have calcium, and then you have potassium, and then you have sodium, and leaving around 2% for the rest of the minerals as far as the crust is concerned. So that's another interesting observation that we need to understand when it comes to the mineral composition of the entire Earth and the Earth's crust. It is very necessary that you compare them and contrast them. Okay, it makes it easier to understand as well, and of course you get a feel of where to find what as far as the whole Earth is concerned, as far as the interior of the Earth also is concerned. We'll have another look as how we tend to divide the Earth as such. We have the physical properties towards the left, and you have the chemical properties to the right as such. We see that the lithosphere, that's the brittle solid, and then it is followed by a ductile solid, which is called as asthenosphere. A ductile solid would be a more appropriate word. Yesterday we spoke about, somebody asked me a question that when you say plastic, what exactly does this mean? Okay, a solid which can be molded, which can be folded, is called as a plastic. So ductile solid would be a more scientific word which we can use for asthenosphere. The outer core, of course, is liquid, and I think the arrows are wrong here. I borrowed this from the net, and I see the arrows are wrong. I need to correct this. Please remember that mesosphere is basically mantle and not the inner core. And inner core is the center, the reddish color as such, and the outer core is the yellowish color. Coming to the chemical properties as such, we have seen this earlier also. You'll see that the crust, the average composition, 47% is oxygen. We've just seen it. 27% is silica. 1% here and there will always be there. 8% aluminum, I think that matches. 5% ferrous, I think they had 4 there. Calcium, magnesium, potassium, and sodium. What is important is that the major minerals, all of them, irrespective of the percentages, the major minerals have come up here. Okay. The mantle you'll see is composed of silicates, which are rich in rocks and manganese, and the density we have seen is around 3.3 to 5.7. And the core is made up of iron and nickel alloys. The density is between 10 and 13. And of course, we have said this, that the continental crust and the oceanic crust, they have different densities as well. The oceanic obviously is going to be a bit, I would say, um, more dense when we compare it to the continental crust as such. Let us move ahead. And two more things that we need to look into. These are just revisions, but yes, they are important. Okay, data as far as the interior of the Earth is concerned. Once again, you'll see that the crust is 30 kilometers, the upper mantle is 720 kilometers, and lower mantle is 2000. Now, invariably, what I see students doing is they divide, and in fact, in many diagrams also, I would not blame the students as such, but in many diagrams that are there, even on the Google, you will see that the upper and the lower mantle are more or less seen to be divided equally. But remember that it's the upper mantle is around 720 and lower mantle is around 2000 kilometers. Of course, off late, people are finding further more discontinuities within it. Obviously, when you go into super specialization, people will come up with more inferences as such. The outer core is around 2000 kilometers. The inner core has a radius of around 1200 kilometers. An approximate number of the radius of the Earth would be around 6400 kilometers as such. Looking at the densities towards the top, the density in the crust is 2.2 grams per cubic centimeter. By the time you go to the base of the crust, it is 2.9. It's as far as the upper mantle is concerned, 3.4. At the base of the upper mantle, it's 4.4. Lower mantle starts at 4.4 and it increases up to 5.6. Outer core starts with 9. So this is the quantum jump in density between lower mantle and the outer core as such. No wonder it's in a liquid state. And in spite of the fact that, of course, there is a quantum jump as far as the density is concerned. By the time you go to the base of the outer core, it is 12.2 grams per cubic centimeter. As far as the inner core is concerned, it starts with a density of 12.8 grams per cubic centimeter, and it goes to around 3.1. What type of rocks would you find? Obviously, we've just seen the chemical composition, the mineral composition. So it's going to be silicic rocks. Okay, most of the rocks are going to have some part of silica. You had andesite. Andesite is basically making up the it's a heavier form of igneous rock, and it is found at the ocean basins. Basalt is also found at the base. So upper is going to be silicic rock. The lower part of the crust is obviously going to be andesite and basalt. Then you have olivine and garnet and pyroxene, which make up upper mantle. Okay, inner mantle is most of silicon oxides and magnesium. As you go into the core, it's iron plus oxygen, sulfur, and alloys of nickel, and so on and so forth. So if I would say that if I add the graph of, if you're making your own notes, if I add the graph numbers of temperatures here, this would be an complete table, I would rather say, to speak on the interior of the Earth. All you have to do is add the temperatures in degrees Celsius, of course, to this. So that is as far as the interior data on the interior is concerned. Just to another view into that, you'll see that physical properties, you have the atmosphere, hydrosphere, and then you have the lithosphere, and then you have the asthenosphere. So see how the grading has taken place according to density. The least density atmosphere, followed by a higher density, that's hydrosphere, more density lithosphere, further more density, okay, but ductile is asthenosphere. You go further down, you have the outer core, which is liquid, and of course then you have the inner core, which is again solid as such. And as far as the density is concerned, now here you'll see that there is a bit of change as far as the density is concerned as regards the table here is concerned. Here, the inner core density stops at 13.1. This diagram is a liberal diagram. It says it's around 16 towards the core and 14 at the outer core. Okay, of course, made up of iron and nickel, stays to be there. The total radius of the Earth is 6,371. As I said, this could vary according to an individual who, it's from where you're going to measure the distance to the center of the Earth, which is going to be more important rather than anything else. So these are basic informations about this. Then, how is the Earth placed? You'll see that again. Here you have the temperature thing. You can carry it from here. You'll see that at the base of the asthenosphere. We said asthenosphere is 1200. At the base, that's the deepest from where the earthquakes occur, 700 kilometers down. It's 2000 degrees centigrade, and then it increases 3000. And by the time you go to the outer core, 3800 degrees, and at the inner core, it's around 6000 degrees centigrade as such. And this makes these movements, okay, the temperature, the convectional movements happen because of that, because the more the temperature, the more it tries to liberate itself, and so on and so forth. Okay. The cycle of heating and cooling of the mantle. Okay, it's the mantle wherein this transfer of heat takes place in a convection. You can see these, the white ones are basically the energy which is coming up, and the dark arrows are basically the low temperatures which are going back, and that's why that makes the mantle very interesting. I would say as interesting as the crust, we would rather say. You have currents of heat which arise in the mantle, and then you have to supplement that, you have heavier ones which dip down into the interior parts of the mantle. A cycle of heating and cooling in the mantle combined with the force of gravity causes this, say the huge plates on the Earth to fracture and move, and which is eventually called as plate tectonics. That is what we need to remember. Then here is where the most interesting part of the study as far as the interior of the Earth is concerned, because more than 90% of what we know as far as the interior of the Earth is concerned comes comes from our research on earthquakes, seismology. You'll see that all these people, Gutenberg and Hugo and Lehman and Conrad, all these were working on earthquakes, and that is how they could give us all these things as such. Okay, so this is a paper which was I've purposely put it here basically because this is a research paper which is published in the IRIS. Okay, those who are interested could go into the details, and that's why you'll see that I've put up this paper. It's latest one, and it's exploring the Earth using seismology. How do they do it? I've purposely put up a diagram that you generally used to have in your geography texts when you were in school. Okay, this was a very interesting diagram, and I've seen that invariably geography teachers, because they don't understand much of physics into it, they skip this diagram, and the only question posed on this is possibly what is the shadow zone. Okay, now if anyone asks them why actually shadow zone occurs, it becomes very difficult to explain. In fact, you will see that we need to understand it in a very peculiar way. Before I start, okay, I would in fact reserve it. I don't think I should be starting it today and I just introduce this very slide, and then the next time we meet, that's probably next Thursday, that we would go into the details of understanding how seismology is used and what actually is all the part of seismology. A few things that I would like to tell you, that normally seismic diagrams are shown like this, isn't it? Now that does not mean, some students in fact asked me a question, that is it that the earthquakes, the epicenter of earthquake is at North Pole? I was nearly to say that that is a foolish question, but then I remembered that in most of the diagrams, you will see this happening in that particular way. And that is why a misnomer that crops up with students of geography, that earthquakes should be for coming up. Of course, this is not true, we all know. But then that is how misnomer spreads, isn't it? There are two terms that we have to keep in mind, the focus and the epicenter. where the earthquake originates in the earth. That could be in the crust, that could be in the mantle, that could be deep into the mantle. Okay, where it originates, it is called as the focus of the earthquake. And while it originates, the shaking starts there, and thus the shaking comes up all to the surface. And when it comes to the surface, the point at which the shaking strikes first, and this invariably geometrically is the point which is exactly above the focus, that is called as the epicenter. Focus is in the interior, epicenter is the point at which the shock waves say come first, they're experienced first, that is called as the epicenter. And let me tell you that earthquakes can happen anywhere. Like in the diagram, we adjust this diagram in such a way that we show epicenter at 12 o'clock. It does not mean that earthquakes occur at 12 at the North Pole. This is not the North Pole. Okay, we are adjusting earthquakes to 12 o'clock in the clock. Okay, now a few things that I would like to uh, show you all here is that you can see 90 degrees mark, that's a right angle. And then the shadow zone starts at around 103. Now some textbooks will tell you, some reference books will tell you 102 degrees, 243 degrees. Now what exactly is the shadow zone, etc.? We will understand it only when we have understood other things as far as this is concerned. And that is why we need to look into this aspect also. Earthquake waves come in three forms basically, which are further subdivided. You have the P waves, okay, you have the S waves, and then you have the surface waves. And as the diagram goes, as the waving goes, okay, you'll see that surface waves are seen to be most destructive. Because P waves and S waves are not that destructive, they are helpful for us to understand the interior of the earth. How are we understanding the interior of the earth as such? You'll see that this is the P waves, this is the S waves, P waves, P waves, and there's P waves here. You'll see that you don't find the S waves here. The S waves, the limit is here. So that is why the shadow zone starts here. I'm going to go into the details next time. I'm purposely not going into the details because it needs to be understood in a context. And I purposely put this diagram also, that now, though the earthquake is matched at 12 o'clock, you can see that behind that, on the surface, you can see that this earthquake has occurred somewhere in the United States and not at the North Pole. So this is how they tend to understand this as such, and this is how they have recorded it as well, that the P waves will come the first. After 10 minutes, you'll have the S waves, and then the 20 minutes, you have the S and the PKP waves. Of course, we don't have to go into the details of that, but half of the major destruction starts after half an hour, when the surface of the ground waves get active as such. Now, what happens with them is basically understood in these diagrams. I don't want to confuse you all further. You can just keep this in mind for you all, and next time we meet, we'll go into the details one by one. I think I've uh, reached 50 minutes of our talk today. So I would stop my sharing here, and I would end this, and let us take up a few questions if you have anyone with you all. I don't see any questions right now, but if you have any questions, Kruti Merchant, Sarvade Swapnil, and Anjali Irkal have joined later. Um, yeah, if you have any questions, you can just ask these questions, or else we are coming to the end of our um, session for the day. Yeah, if you have questions, you can just type them, and let us see if I can answer them, or I'll get the answers by the next time we meet. I give this time basically because I know there is buffering, there is say of the relay or the live stream, and you may have questions after, or you may receive the broadcast with a lag of time, and that is why I tend to wait so that you get the point and then you ask me your questions. As I always say, that you can ask questions on the WhatsApp group as well. If you come up with a question later, it hardly matters. You can still ask me your questions on the group as also. Well, if we don't have any questions as such, I will wait for questions. Even if you post them afterwards, I'll just come back and check the comment section so that I would be able to read through your questions if you have posted any. That's all for today, I would say, and I would be ending my broadcast. Have a great weekend. Stay home, stay safe. Yes, particularly after Diwali, if you read the statistics that are coming out, Delhi is already experiencing spikes as far as corona cases is concerned. Let us see that it does not happen in and around Maharashtra and Pune particularly. Let us not be super spreaders. Let us stay back home safe and keep our home members safe. Okay, stay home, stay safe. Have a happy weekend. I'm ending my